This is the lecture for Chapter 3, Histogram PowerPoint. This is a continuation of where we picked up from last class period. This segment covers the histogram, the lookup table, automatic rescaling. This is only part 1 of the PowerPoint presentation. If you remember, we talked about the difference between pre-processing and post-processing. With CR and DR, after the image has been captured, it has to be converted into an electrical signal. These electrical signals are then available for processing and further manipulation. Pre-processing takes place at the computer, where certain algorithms determine the histogram, which we'll talk about. Post-processing is simply done by you or the technologist through different workstation functions, which we've talked about. Okay, so let's dive deep into the histogram. If you recall, we have talked about this matrix. The matrix is made up of various pixels, and the pixels have a bit depth. The bit depth tells how many shades of gray that particular pixel can demonstrate. But in a more simple explanation, each pixel, which is part of the matrix, has a specific number assigned to it based on that intensity value. Darker colors or darker shades are given a higher number, where lighter shades are given a lower number value. A histogram then is a graphical representation of this matrix or these formulations of different intensity values. So the definition of a histogram is a graphical representation of exposure values collected off of the imaging plate following an exposure. The value of each tone is on our horizontal or x-axis, where the number of pixels in each tone is represented on our y-axis or our vertical axis. Now, for S numbers, and if you pull up this PowerPoint, I do have some notes that are typed in below here. But for S numbers, the values to the left are darker, and values that aren't quite as dark are to the right. These would be brighter tones. This picture comes out of your textbook. Now, this is again only for S numbers. If you recall, S numbers are an inverse relationship. So a higher S number indicates a lower exposure, and vice versa. Again, this is how your textbook explains this concept, and this picture comes out of your textbook. So here's a picture of a histogram. Again, we have our exposure or density values versus the number of pixels on that image that have that particular exposure or density value. This is how the histogram is normally displayed. We have peaks and valleys, and it's not so graphical. This is a picture that comes out of your textbook as well, and this is a chest x-ray, and it's just an example of a histogram. Again, these are S number values. So areas to the left represent darker shades or darker areas on the image. You can see we have various peaks and valleys. Areas with high attenuation, which would be brighter, such as the mediastinum, are to the right. Areas with low attenuation, such as the lungs, which is a little bit darker, are to the left. Again, this is S number only. All right, so let's look at a real-life example of a knee. The following slides show an example of a knee, and these examples use a direct relationship. So this is not going to be S number. Rather, these are going to be exposure index or LGM numbers. So on this knee, we have areas of high intensity versus areas of very low intensity and normal densities. And then here's just the graph that's explaining how this would look in a histogram format. Again, areas that are darker have the great peak to them here, and it's not a very large bump, if you will, because we don't have too many areas that are of great exposure. C was the good densities, so this represents kind of the main chunk of the histogram, and B is the brighter areas, so this is just a very short or small area on the histogram. These are directly related, So areas that are more intense or that are darker, received more exposure, have shifted more to the right side of the histogram. So with processing of a CR image, the whole entire plate is scanned once it's inside of the reader. The image location and the orientation of the image, such as crosswise, lengthwise, is then determined. The size of the signal is determined, how dark, how bright it is, and a value is placed on each pixel. A histogram that's then just gets generated from this image data. So a histogram shows us everything between the minimum values and the maximum values, and it identifies all densities on the plate. Again, the x-axis is the amount of exposure. The y-axis is the number of pixels that has that exposure. This is one by Kodak. You can see a chest x-ray, and then here's the histogram that goes with that. The peak here is direct area exposures, so this dark area here. The middle hump are the areas of lung exposure, and then the areas to the left is the mediastinum and heart, which are brighter values. If you recall from prior discussions, we said that digital image receptors are able to record a wide range of X-ray exposures. Again, the Bounty paper towel. When we go to form that image, if we use the values at the high and low ends of the exposure, we would have a poor resolution image. It would just almost be too much information overload to create that image that we see. So to avoid this from happening, exposure data recognition processes only the optimal density exposure ranges. And it knows how to do that based on information that has been programmed into the system. So data recognition programs, again, recognize the anatomy. They find the edges of the collimated border, and they exclude the information outside of this collimated border. Everything within that collimated border then is used to form the histogram. Information within the collimated area is what we use to form the image. And then we receive our LGM number, our S number, or exposure index number based on what it finds inside of that collimated edge. This is just an example of where an image has been taken. It did not use the entire exposure plate, and the collimated edges were determined. Now this one is somewhat skewed, and I would advise against skewing a CR image because sometimes this data recognition becomes difficult for the system. So ideally, in a perfect world, all 4 edges of the collimated field are identified. If 3 edges are not identified, then everything on that plate gets included in the image, such as scatter, off-focus radiation, maybe areas that had raw exposure, maybe the areas that had your lead apron over it gets included in the histogram. This can result in a histogram analysis error, meaning your images will be maybe too bright or too dark, which kind of trickles down to having an incorrect exposure index value, even though you might have used the right KVP and mass. Histogram analysis errors are more common with CR than DR because with DR, only the area that you exposed relates to what gets processed. Now, if the exposure field is not accurately recognized, the histogram is going to contain data outside of the exposure field, which widens the histogram. I would suggest to you to pull out your old image analysis textbook from McQuillan Martinson and refer to Chapter 2, which talks a little bit more about this. Additionally, what's also important with the CR reader is to center your anatomy on the plate. Not doing so, again, could result in an histogram analysis error, an image that is too bright or too dark. Further, you are never to place more than one image on a plate at the same time. Technique has a major impact on the location of the histogram. So KVP changes can affect both the location and the shape of the histogram, where mass affects the location. KVP can result in an image if it's too high with higher density. We've talked about this. Also, high KVP can result in an image with more gray tones, a longer scale of contrast. The histogram would then shift to the right. As there is very little difference in the densities, the histogram is also more narrow. And again, this is for Kodak and LGM numbers because they're directly related. So here we have our normal histogram. Here's an image that was taken with probably too high of a KVP. You'll notice that the graph or the histogram has shifted to the right compared with the normal, and it's a little bit narrower compared with the normal. It's narrower because, again, with a high KVP, there's very little difference in the densities, which makes the histogram more narrow. Here's an example of a very low contrast chest image, very poor quality. There's very little difference in the densities, so the histogram becomes very narrow. By opposition, using a low KVP gives us a shorter scale of contrast, this image to the right. There's more difference between the densities. We have a shorter scale of contrast, it's more black and white. What happens then is our histogram would become wider. Normal histogram on the left, low KVP here. Our graph has shifted over the lower density values towards the left and is much wider than the normal. Mass affects the location of the histogram. It puts the histogram over the lower densities to the left. High mass will place it to the right. This would be opposite if you're using S number values. In the shaded area here, we have a normal histogram. If you follow the line here to the right, this is an image with too high of mass. We have shifted over the higher density values. If you follow this line, we have shifted to the left. These are lower density values. So CR can adjust for most density issues with post-processing, but it cannot fill in an acceptable level of detail if we don't have the proper mass used. Remember, too low of mass results in quantum model. Here's an example with quantum model. We have an image that's very underexposed. Although the density was compensated for, we have a proper density here, it's still very mottled looking, and no CR processing can fix that. It would require a repeat. So in summary, KVP affects the shape and location of the curve, while mass primarily affects the location of the curve. The more your technique deviates from what you're supposed to use, meaning either you use too much or too little technique, it's harder then for the computer to make it have the appropriate density and contrast, which results in less than optimal images. So the histogram analysis is very complex, but the shape should stay fairly constant for each part exposed, meaning it's anatomy specific. So the computer analyzes the histogram using processing algorithms, compares it with a pre-established histogram, which is comparable to a part that you're imaging. This is called histogram analysis. So you're going to pick the exam and the projection or part or view that you're performing. I'm going to end this lecture here, and part 2 will pick up on slide 34.